It looks like we have 3 problems from lesson 7 to look at, and one that was a great suggestion to look at from lesson 5. Now that one is, I think, it's looking awfully familiar, so I think that's one that I did and made a video for because you guys had asked for that on Friday. And so I made this video over the weekend and linked it up. So on our Google Classroom, under our Unit 4 practice answer keys, I should take this time to say this too. I've been putting on any of our video lessons here. So we've had some of our lessons that I had beforehand, but some that we've done in class where I was recording some of our class lesson videos. It's both in both of those places. So there is a video already there about the 2 that you guys asked for on Friday. And it's just me going through lesson number 5, problem number 4, and lesson 6, problem number 6. So that is there for you. I'll invite you to check that out there. That's exactly the one that was asked for from lesson 5. So that's set there for you to take a look at. Well, let's see what these other 2 are looking like. So, or other 3. Ooh, I lost my screen. There we go. So 2, 3, and 5. Let's take a look at 2, 3, and 5 together. And we'll kind of go through these. They are more practice with our half-lives, so some fantastic questions to review as we've been talking about half-lives and exponential functions. So we'll take a look at these together here. Oh, number 5 as well, Taylor? Awesome. Good, so a couple votes for that one. Alrighty. So our half-life of carbon-14, that's one that we tend to use most frequently because I recognize that 5,730 years. Our half-life of carbon-14 we know, and so when we're thinking anything at all about half-life, we're always going to have a starting amount. Our growth factor is always 1/2 for a half-life. And then we're going to think about how many years in one half-life cycle and the number of years that we're going to give whatever it is that we're trying to date some time that has passed. So I've already started to set up an equation that might be helpful for it, but I don't know much more yet than we're doing a half-life and how long it takes for one half-life to happen for carbon-14. A tree fossil was estimated to have about 4.2 picograms of carbon-14 when it died. So there's our starting amount of how much carbon-14 it had when the tree died. And now we're trying to figure out how many years it has been dead if we have 0.5 picograms left. So our starting amount of 4.2 times a half-life, so the growth factor is 1/2, it cuts in half every 5,730 years, equals now 0.5 picograms. This is exactly what scientists use as they're trying to carbon date this. So I need to start isolating my variable up here. Right now, the farthest thing away from it is this 4.2 that's being multiplied. So I'm going to divide both sides by 4.2. And I need a calculator to see what that's going to be looking like. 0.5 divided by 4.2. So I have to think about 1/2 to some kind of exponent of getting 0.119. Now, we don't have the skills or strategies yet to solve this. Notice I'm saying yet because this is actually where we're going to start working today as we move towards how we could solve things like that when we don't know the exponent. So right now we might be stuck on something a little more like figuring out how many times we have to multiply 1/2 to get to 0.119. So I'm going to take this 0.5. If I multiply it by itself 2 times, so to the second power, we're at 0.25. Times 0.5 again is 0.125. That's getting pretty darn close to that. So that was x to the 1/2 to the third power. We multiplied it 3 times. I'm going to try it just one more and see if I get closer to this 0.119. Oh, that's too far away. All right. So if I did 0.5 to the third power, we got pretty close to 0.119. I'm going to say, since we're just estimating right now, about how many years ago did that happen? 1/2 to the third power equals 0.125, and here we're looking at 0.12. So that's pretty darn close. So what this is telling me is I would need 3 half-life cycles or I could set our 2 exponents equal to each other. So this y over 5,730 has to equal an exponent of about 3. Either way, I'm going to be multiplying 5,730 by 3 to figure out how many years it has been. 5,730 times 3 sets, or 3 rounds. This thing is about 17,190 years old since the tree died. So we're just getting kind of close there. We're just estimating what that might be. And that matches up really nicely with what answer it gave in the answer key, this 17,190 years old, for that same reason. So we had to set it up, we had to do a little guessing and checking. We're going to see how we can get way more accurate with that in today's lesson and tomorrow and really the whole rest of the week. Any leftover questions on number 2? All right, we're going to tackle number 3, go a little bit faster because it's that same kind of idea. Nickel-63 is a radioactive substance with a half-life of about 100 years. So this one now is cutting in half. And when I think about how many years we're going through, I'm going to divide that by 100 because it takes 100 years for one cycle. An artifact had 9.8 milligrams to start with of nickel-63 when it was first measured. So there's a great starting point, 9.8 milligrams. We already know a growth factor of 1/2. And if we're just looking at time in years, well, we already wrote that idea. Whatever our time is in years, we're going to divide that by 100 because there's 100 years in one cycle. So if I put 1 over 100, I would get 1 year out of that 100-year cycle. And to convert this into days, I'm going to have the same starting amount because I haven't changed the starting amount or the growth factor. All I'm changing is the units up here into days. So instead of 100 years, I need to convert that 100 years to how many days it would be. 100 years equals well, 1 year equals 360 days. 365, sorry. 365 days. So 100 years would be 365 with 2 zeros after it. 36,500 days. So if I just want to know a single day, I'm going to use D for days and use that conversion of 100 years converted into how many days it would take for one cycle. So we can just change the units just by thinking about how long a cycle is in whatever units we're looking for. We could even convert this to hours and minutes. I don't know that we need to ever date a tree that specifically, but if we wanted to, we could. Nice. And one last one to look at from our practice problems. People asked in lesson 7 to look at number 5. An excellent one to look at because we're going to interpret some values and information. So a population in a city is modeled by an equation given here. D is the number of decades, so I'm going to keep that in mind. And when we're looking at what does the 0.3 and the 100,000 represent, that 0.3, if our multiplier rate would be 1.30, that 0.3 is showing how much it is growing. The population is growing 30% per decade. I know this because it's keeping 100% of its population and it's adding 0.3 to it. It's adding 30% on top of that 100%. So population is growing 30% per decade. The 100,000 is in our starting amount position, so it's our starting population. In the year 1970. Now part B and C are just like question 3 that we just looked at. We're just changing units. So it's looking for years instead of decades. So if I wanted a year instead of a decade, I would still have 100,000, our starting population, 1.03, our growth factor. And if this is every decade, 1 decade is 10 years. So I could then have it divided by 10, so I could figure out how many years it was. That means if it's more than a decade, if it was 20 years, it would be 2 decades. If I put 20 over 10, I would get 2. To show 2 full decade cycles. Or if I only wanted 1 year, it would be a fractional, because it's a fraction of a decade. This then asks us to represent it in centuries after 1970. Now centuries is telling us that instead of a decade, we're going to go longer. So 1 decade is 1/10 of a century. So I'm going to take decades if I'm looking at converting it to 1/10 of a century. I don't want less than a decade. I want more. So this 1 decade that I had up here, if I'm converting it to a century, I would have to divide that by 10 and be thinking of what that might be. So we would have 100,000. Still our multiplier 1.03. And now if I'm looking per century, I've got that, I'm sorry, not 03. Oh, I keep on writing that. Please forgive me. There shouldn't be a 0 in there. My bad. It's just 1.3. I'm thinking that it's only growing by 3%, but it's growing by 30%. So sorry about that. So if we went to something smaller, we had a fraction of how many years we were doing it, but this time we're going by certain centuries, so we would have to, instead of going to a fraction, we would want something bigger. We'd have to take 10 times our decades like that to convert it to centuries. So if we were looking at how many centuries it was going along, we'd have 1.3 C for every century that we're looking at. Just like we put it as a fraction y for years, we would end up having it as something larger. If we're going bigger in timeline, we would need it as a multiplier greater than 1, something making it longer. So there we go. If we knew if it was then a whole, what portion of a century, right? A decade is 1/10 of a century. So we'd be back to a 1 over 1/10 of a century going on, and that would put us to the first power. So some nice ways we can convert just by changing them to bigger or smaller exponents based on our timeline. Delightful. De gorgeous. De perfect. All right. Thank you for those couple questions. Those were really good ones for us to review. And we're going to look at our lesson 8.3. This is the only part of lesson 8 that we're going to tackle when we have these unknown exponents. It's going to help us lead really nicely into lesson 9 and the second half of our unit. So we're already making some fantastic progress through this unit. And we'll see now that we have this idea about how exponents work and exponentials, where we have an unknown exponent that we're looking for. Our goal here in lesson 8 is to see how we might start solving unknown values when we don't know the exponent. So 8.3 gives us this situation that we have a lab where a colony of 100 bacteria is placed in a petri dish. The population of that bacteria triples every hour. So that sounds very much like a starting amount and a growth factor. 100 bacteria is what we're going to start with. And if it triples, there is our growth factor. And it does that every hour. So the first question that we have here is using some known timelines, so some known exponents. If I wanted to find the population of the bacteria in 4 hours, I would start with that 100, use my growth factor of 3 because it's tripling, and if it's doing that tripling every hour, and I give it 4 of those hours to triple, we will bring it up to the 4th power. So every hour it triples. Over 4 hours it's going to triple 3 times. So 100 times 3, 4 times. So 3 to the 4th power. Love it. Yep, going to need a calculator on this one. And on all of it. Noah, I'm going to ask you, when you have an answer for this one, would you please let us know what that answer is? And we're going to see if Emma Dibble agrees with you or disagrees. Let's hear what Noah has to say for his suggestion for an answer and see if Emma agrees.
I'm not sure if this is right because I don't have a graphing calculator, but I got 81.
81. All right. Let's see if Emma agrees with that. Emma, how about you?
I got 8,100.
All right, 8,100. I think that's where Noah's getting that 81 going on. So that 81, but we're talking about starting with 100, so it's got to be bigger than 100 starting amount. So Noah, I think it's just 8,100 or 8,100.
Yeah, I did it on my phone.
Gotcha.
It's
All right, awesome. Thank you for that. Very nice. All right, so after 4 hours, we have 8,100 bacteria. After 90 minutes, now be careful here, they changed units on us again. Our tripling is happening every hour. They want us for 90 minutes. If I converted 90 minutes to an hour, how long would that be? Nice, an hour and a half going on. So we'll look at this as 1.5 hours. So 100 times 3, same growth factor. This time we're only going to give it an hour and a half to grow instead of 4 hours. We're going to see what Logan says about this one when he does that calculation and then see if Kennedy agrees or not. You got what? 519.6. Kennedy, did you get the same?
I got the same thing.
All right, very nice. Fantastic. So we're getting some great answers and seeing how we can change the timeline. I hear people already pressing on buttons and getting ready for our next one. If we're only going to give it a half an hour, we would only need to bring it up to the 1/2 power. Avi, would you share with us what you have for your answer on this one? 173, nice. Madison, did you get the same?
Yeah.
All right. We got students getting the same thing. It's got to be right. Yeah, 173.205 or 21. Nice. So we'll always go to like 2 decimal places if we can, 3 if we need to see even more. So this is where we're going to get into kind of the next challenging phase on this. On the next page, on page 196 for you guys. This is where we're starting to see an unknown exponent. And we saw one of these in our practice problems where we didn't know how long it was going for. We had to kind of estimate it and see if we could figure it out. So if we had to estimate the number of hours it would take for our equation to start at 100 bacteria, triple for an unknown number of hours, and end up at 10,000 bacteria, we don't know the exponent in this case. But we could use some math to start moving some things side to side, just regular algebra that we've been doing in the past. We have 3 to an x, but it's multiplied by our starting amount of 100. So if we divided both sides by 100, I need 3 to some exponent that's going to equal 10. And And if we just need to estimate this, we're not looking for specifics. This kind of reminds me what we were looking back kind of in Unit 3 where we're like, well, it's going to be between this number and that number, right? 3 squared equals 9. 3 to the third equals 27. 10 is in between these, but look at how close it is to 9. So our exponent is going to be between 2 and 3, but it's going to be really close to 2. So if we had to kind of estimate what that might be, we know it's going to be a little bit more than 2. Maybe it's just like 2.1. And we could then turn to a calculator and see what that started looking like. If I have 3 raised to the 2.1 power, oh my goodness, look how close we got. 10.05. That's amazing. And if we wanted to see how long it took for the population to double, to get from 100 to 200 is what our population target would be. We could start to solve it and get an estimate. 3 to the x power is going to double the population. 3 to the 0 power is 1. 3 to the first power is 3. So it has to be between 0 and 1 for our exponent. 2 is smack dab in the middle between 1 and 3. So I'm going to guess it's probably something very close to the middle there. I'm not quite sure, but it'd probably be something like maybe 0.5-ish. Maybe a little bit more than that. Let's see. 3 raised to the 0.5 is 1.7. So I'd have to go a little bit more than that. Maybe it's 3 to this 1/6 power. That's a little closer. 3 to the 0.7 power is too much. So we could say with the guessing and checking, x is close to 0.6. With a little guessing and checking. But we're going to see in the second half of this whole unit how we can get way more specific than that, thanks to a math operation. So we can figure that part out. So it's getting us to start thinking kind of backwards and how we can take a known amount and start to change it up and see what we'll be looking at for it. Let's jump into lesson 9 and see what that is that we're going to be doing. Lesson 9 is called What is a Logarithm? So to learn about logarithms, that is exactly the function that we're going to use. It's like a math operation, right? It's just like multiplication, division, subtraction. It's just like using sine, cosine, and tangent. It's an operation that we can use that our calculator will do for us. So a logarithm is a math operation that isolates an unknown exponent. Some unknown exponents we do know because of our math knowledge. Can you tell me 4 to what power is going to equal 16? 2. Nice. To the second power. What about 4 to some power equaling 2? Nice, the 1/2 power. Nice, looking at a square root going on here. So the square root of 4 equals 2, and that's the 1/2 power. Thank you, Unit 3. We can calculate this part too. Now we know like 4 to the 1/2 power equals 2. So we can take 4 to the 1/2 power and then raise that to the 5th power. That's a way to look at 4 to the 5/2, or you could type it in a calculator and calculate what that is. Because 4 to the 1/2 power, you guys just told me, is 2. And 2 to the 5th power, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And so 4 to the something power equals 56. So we could kind of sit here and guess and check of what that might be, or we could maybe take some of our known ones. But a logarithm is going to help us isolate that exponent all by itself. You ready to see how it's going to do this? On your calculator, there is a function that is called log. You see that here? It's next to the number 7. On our TI 30s, it's up here at the top. We are going to use that log. It's short for logarithm. And what it is a way to isolate your exponent by itself and type it into the calculator. Right now we have a base 4 to exponent d equals 56. Base 4, exponent d equals 56. A log takes that base, pulls it to the other side to get the exponent isolated. So d would be by itself. Log makes that happen. It's in base 4. So we're going to have a little sub number, a little smaller number, a little bit down below. And then 56. Now you're probably like, well, how do I type that in the calculator? Because on here, if I just hit log, it's just like opens a parentheses. And on here, if I hit log, it's just going to open parentheses again. So the way that we enter this, because our calculator struggles with doing a base number, on our graphing calculator, it is in, and I have to remember where. Not in any of those. Oh yeah. There we go. It's in our math menu. So on your graphing calculator, and it's not even in all of them either. If you hit the math menu and scroll down, you will see one that says log base. And mine then gives me two little boxes that I could put in a 4 and then arrow over and do our 56. If you are using one of our smaller calculators, or if that is not intuitive, which it's really not, here's how we type it in a calculator. Once we can write it in this form, we're going to do the log of 56. And then divide it by the log of 4. So we saw we could do it here in graphing calculators, but if you're working with something that's not quite so fancy, even a cell phone calculator has a log button. We could do log of 56, close those parentheses, and then divide it by the log of 4, close parentheses. And we get the same answer, 2.9. So a logarithm isolates an exponent all by itself so that we don't have to guess and check like we were doing in the last question we just did in lesson 8. We don't have to guess and check. We could find an exact decimal that it would be, and we can find it very quickly. So logarithm is a math operation that isolates an unknown exponent. We can see a lot faster now how long it takes something to decay or to break down or to grow. We can now use this to make estimates of how much time we have before a population gets to a certain number, right? Remember we talked about like having to build schools if our population is growing. Now we know how many years we have until we hit a certain population that's going to need a new school. Now lesson 9 on the next page. This is the old way of doing things. They used to publish entire books of logarithms and sine, cosine, and tangent. And it was just filled with tables and charts just like this. Because they didn't have calculators that were smart enough to do it for them. So someone figured this out by hand, and then they wrote it all down and made a lot of money publishing books for it. And then calculators came along and were like, ooh, we can just push buttons and get it done too. So the way we read this, each of these is log base 10. So it's saying 10 to some exponent equals the x value that you see in the chart. So 10 to some exponent equals the x column. The log columns, this whole column here, is the exponent. So each of these columns is saying that is the exponent we would need to use. So some of our whole numbers are looking really familiar. This is saying 10 to the first power equals 10. 10 to the second power equals 100. 10 to the third power equals 1,000. But we can break it down with some smaller values in between. So 10 to the 1.6990 power equals 50. So before they had calculators, they had these tables upon tables in whole books. It was like the size of a dictionary. And they would just have these for all of these different numbers and values. It was intense. And I'm going to flip forward a little bit. You don't need to go there with me, but I just want to peek ahead because I see in lesson 10 tomorrow, we're going to see that we can change that base. So here they have base 2 raised to these exponents to get to this value. So if we can change that base that we're lifting up to an exponent, now you can understand why it would be the size of a dictionary, right? Because we need base 2, base 3, base 4, base 5, base 10, base 20, base 50. Because we can take anything and raise it to an exponent. So our logarithm is simply saying that 10, there's our base. It's the little number when we have a log with it. 10 to the second power equals 100. We can roll that 10 to the other side, and it kicks that 2 up to an exponent. You kind of see, can you picture that? Almost like telling a story of how that happens. It's going to roll to the other side and kick up to an exponent.
Good morning, students and staff. I want to just